Okay, welcome back, everyone. This session will be about Makeflow, which is a tool which is, in my view, complementary to A-Tools, because we've seen that A-Tools is very handy for job arrays. So when you have collections of jobs that are similar, by contrast, Makeflow is more suited when you have a large number of complex dependencies between jobs. So the goal of this session is to get an overview of the capabilities of Makeflow and of its usage. So Makeflow is a workflow system for parallel and distributed computing that uses a language which is very similar to Make. So GNU Make, the tool which is usually used to build software from sources. So using Makeflow, you can write simple scripts that execute on hundreds or thousands of machines. Makeflow is actually part of a larger ecosystem called CC Tools. And you can see that along Makeflow, you have tools like Workqueues, which I will talk a bit about later on. And you have also tools that are meant to help with the file system, but this I will not talk about. Rather, the topics I will cover are how to install Makeflow, the syntax. We will see that it's pretty similar to the syntax of GNU Make, but there are some differences. And then we will see how to run, monitor, and so on the jobs. And we will see how Makeflow actually interacts with the schedule. Just like with other sessions, do not hesitate to ask questions in the chat. I will try to monitor it regularly. So let's start already with the installation. The way you install Makeflow is actually to download the archive that contains the whole suite of software, which is CC Tools. You can do that with wget, and then you use the typical sequence where you compile from source with tar to extract the source and then configure to prepare the compilation process. And you can there specify the prefix to choose where you want Makeflow to be installed. And then you can run make and then make install, and you just have to make sure that your path contains the directory in which Makeflow is installed. If you have EasyBuild on your cluster, it can be as easy as starting EasyBuild with the correct easyconfig file. So if you ever do that, you should be able then to use module load CC Tools to get access to Makeflow. So this is pretty straightforward and pretty classic. When you need to install software on the cluster, you compile from source. So let's move on to the syntax. Just with Maestro, which I presented a bit earlier, the idea with Makeflow is that you do not need to write the submission scripts. You do not need to know about how to write the script for PBS or for Slurm or whatever. It will just be taken care of by Makeflow. And the syntax, as I promised, is very similar to that of a GNU file, of a GNU Make file. So the idea is that you can write comments. You can write comments like this. So this is a comment that will be ignored by Makeflow. You can define variables. And here you see I define a JZ variable, which will actually be used in the next line as a shortcut for this line. So module load gzip, and that gzip and with some arguments. And then you see exactly like a make file, you have a target, which is a file, and a colon, and then a list of dependencies, which are also files. After that, you have a line which must start with a tab character. And here you see the usage of the gz command with the remaining of the line. And so this rule states that the file archive.tar.b.gz is built from archive.tar using this command. And you see here that I use a --best option of gz, and the dash capital S option to specify the suffix that I want gzip to append to the file once it is compressed. You see also here an example of a second rule that is very similar to the previous one, except that --fast is used rather than --best. Rule 3 here explains how to create archive.tar from a directory named directory in which you have a file named file1.txt, and that is done using the tar command. And finally, the rule 4 here has no dependencies, and it simply states that to create a directory and file1, you use mkd and touch. So if we look a bit deeper at the anatomy of a rule, as I said, you have the output files, which are the targets, a colon, and then the input files or directories. Afterwards, you have the commands that will generate the output from the inputs. The commands must all be on a single line. So this is by contrast with the syntax of Makefile, where you can have multiple lines in each rules. Here, only one line is allowed. So if you have multiple commands, you will need to separate them with a semicolon. You can also prefix the command with local, and that will indicate to Makeflow that even though you might have asked previously Makeflow to submit the commands to a workflow scheduler, to a workload scheduler like Slurm or PBS, you want this step to be only processed locally. And also, final comment is that the rules must be plain rules. Actually, the Makefile syntax is very complex, but the syntax for Makeflow files is just a subset, which I described here. With the addition of variables, so just like in a Makefile, you can define some variables to be some value, and the variables here in this context are scoped, meaning that if you define the variable at the beginning of the file, the value is valid for all targets and all rules. But if you redefine it inside the definition of a rule, it can take another value specifically for this rule. Also, you can specify environment variables that can be set with the export command. When you install Makeflow, you will see that there are other tools that comes with it. Among other, Makeflow_viz, which is a tool that will take your Makeflow file, which I named here build archive.makeflow, and it will create a dot representation, so a file which can then be consumed by the dot command to produce a picture. And this will create a file with a graphical representation of the contents of your Makeflow file, where the targets and dependencies are in the square rectangles, in the blue rectangles, and the commands are in the green circles. So it's an easy way to check the correctness of your workflow, to make sure that the Makeflow file has the same sequence of operations as you expect from the study you need to perform. And also, it's an easy way to communicate about it. It's much more easy to talk about a graph, which you can show to your colleagues, than trying to explain with simply words. You see here that the commands here, for instance, is module. This is because this is the first command that is run on the step that run the gzip command, because I first load the module about gzip. But the nice thing is that since Makeflow_viz creates an intermediate representation, you can hijack it and correct it on the fly if you need. So here you see that I run the same Makeflow_viz command, except that I put a set command between the Makeflow viz and the dot command, where I replace module with GZ so I can actually get a graph that I want. So you can still do some manual corrections if you need. Other tool that is also interesting is Makeflow Analyze, where if you specify the -k option, it will just perform a syntax check, because sometimes you just want to make sure that the syntax is okay and not actually start the Makeflow. The other option, -O, will actually list all the outputs, which is also an interesting way to make sure that the Makeflow file will do what you expect it to do. Okay, so now we know how to write a Makeflow file. We know how to make a representation of it and make sure we know how to analyze it. And the next thing is how to actually run the Makeflow. It's pretty similar to Make, except that it's Makeflow, but you need to specify the name of the Makeflow file. And if you do that with the file I showed earlier, what you see is first a prologue where Makeflow parses the Makeflow file. It gives also the list of local resources it has found, and it looks for consistency, just like the previous tool that I showed. And then it starts the workflow. And what you see after is submitting job, and then the rules of the fourth rule. And of course, Makeflow started with the fourth rule because this one does not have any dependency. You see that it says submitted job and then some large number. And actually, this is a process ID. So at this point, at this stage, I did not ask Makeflow to submit any job. So this ID is a process ID. Going further, when that is done, you see rule 3, which is being started. And you see again, this is a process ID. You see here the output of the rule, and then it says that the step is completed. When that step is completed, Makeflow will run rules 1 and 2 actually in parallel, because they have the same set of dependencies, but there's no dependencies between rule 1 and 2, so they can actually start at the same time. And you see that the start and finish are at the same time. When you start a Makeflow, you will see that Makeflow is blocking. So it means that you will not have your terminal back. You must keep your connection to your submission host or to your login node, or you need to use a terminal multiplexer, such as a screen or tmux, for instance. That is important. If you start to Makeflow, you need to make sure that it will survive some unwanted disconnection. Just like with GNU Make, the second run will do nothing. So based on the timestamps of the intermediate files, Makeflow will only redo a step if the dependencies from which the target is built are more recent than the target itself. So here, the example, I start Makeflow again, and you see that immediately after starting the workflow, it says that nothing left to do. A nice option of Makeflow is to clean for you. So if you start Makeflow with the --clean option, Makeflow will actually remove all the intermediate files that are created in the process. So with the example I showed, what you see is that it has cleaned the file system and deleted all the files that were intermediate until up to the two final targets, which are this one and this one. Okay, so it's a nice thing when you submitted a few steps of the workflow and you don't know exactly what was done, what was not done, and you want to start from scratch, you can run --clean. So this is basically how you run Makeflow on its own. And now I would like to introduce how to make Makeflow interact with the scheduler. So it can be Slurm, it can be PBS, it can be SG, LSF, any. Most of them are possible. We will see 3 distinct modes of operations where either Makeflow submits the jobs or Makeflow runs inside an allocation, and we will have a look at Workqueue later on. So Makeflow will run on the login node, and the typical workflow in this case will be that the user will start Makeflow, and Makeflow will submit jobs to the scheduler. And when the jobs are done, the scheduler notifies Makeflow, and Makeflow in turn notifies the user that the job is done. This is the most classical way of operation for Makeflow. And for that, you just need to specify the -T option. And after that, you specify the type of batch system. It can be local, which is the default, so not using the scheduler. And you see Condor, SG, PBS, LSF, Torque, Moab, Slurm. You see MPI here, because you can actually use MPI as a workflow as a manager. And you see that it can also be used on other type of schedulers that are not that related to HPC, but more directed to cloud, like Kubernetes or Mesos, and so on. There's also a specific scheduler or fake scheduler, which is dry run, where just like you would expect, Makeflow will explain what it will do, but it will not actually do it. So as an example, if you run the same Makeflow file as before, but you specify the -T slurm here, you see again a prologue where it states the local resources it has found. And then when it starts the workflow, you see that submitting job, and this time this really is a job ID in Slurm. Again, since only rule 4 does not have dependency, is the one that is first started. And then afterwards, rule 3 is done, again submitting a job, and rules 1 and 2 are then submitted in parallel. So since they have the same dependency and no dependency between them, they can be submitted in parallel, which does not mean they will actually run in parallel. This will depend on the load and on your priority for your jobs, but they will be submitted in parallel at the same time. So once you have run this command, you can have a look in the accounting, and you will see that Makeflow has submitted 4 jobs with names that it created by default with 0, 1, 2, 3. You see the state, and you see here that the last 2 jobs were started at the same time. So they were submitted at the same time, and here it happened that the cluster had sufficiently enough free resources for them to start at the same time, so they actually started at the same time. So by simply specifying -T slurm, Makeflow has organized all the dependencies between the jobs and make sure that for each rule, a job was submitted and the job was submitted in the correct order. I was talking a bit earlier about all the different types of, about some of the tools that come together with Makeflow, but here's one more. This one is called Makeflow Graph Log, and it's based on the Makeflow log. So whenever you start the Makeflow command, Makeflow will start the log where it will record every step that it does, every job that it submits, and it will take back, it will also log some information about how long the jobs have been running and waiting and so on. And this program can produce a timeline of the whole workflow. And so it's a file and picture like this, where you see here the time, and you see the number of submitted jobs, number of running jobs, and number of completed jobs over the course of time. So this is interesting when you have a large number of jobs to see how the cluster can absorb your workflow. Of course, here the picture with only 4 jobs is not as relevant, but when you have a large and complex workflow, it's always nice to have an idea of where the time is spent. Here, as I only specified dash capital T slurm, I didn't say anything about the type of jobs that I wanted to submit. But Makeflow allows you to specify some variables which are taken by Makeflow as a specification of the job. So for instance, word time with a number of seconds here, a memory in megabytes, or a number of cores being in this example 4. You see that here, as I mentioned earlier, the variables are scoped, so I can actually redefine for this step only the number of cores that I want to use. And here I just specify I want 8 cores rather than the default 4. So there's a question here: is it possible to run Makeflow locally and then use SSH to submit the job remotely? Not as is, because Makeflow will actually look for the sbatch command on the machine on which it is running. So unless there is some convoluted way to make it think there's a sbatch command available, and actually the sbatch command would SSH to the cluster, it's meant to be run on a submission node or a login node. Of course, Makeflow will not have an equivalent variable defined for every option of every scheduler out there. So actually you can use the batch options variable, where you can simply list all the options that you want that are specific to your scheduler. So here I say that I want 4 CPUs, 1 GB of memory per job, and that the partition to which the job must be submitted, which is the equivalent of the queue in most other schedulers, is named debug. You can also specify the batch options on the command line, like this, with dash capital B, and then here again the same line. One thing that is interesting is that by default, Makeflow will copy files between the nodes, unless you specify that there is a shared file system. And that is done with the -- shared file system, where you specify here as example that /home is shared and /scratch is shared. So this is the first type of operations and type of interaction with the scheduler, is when Makeflow submits jobs to the scheduler. So my answer previously about running Makeflow locally and using SSH to submit the job, my answer is specific to this mode of operation, but we will see other modes of operations where actually this is possible. A second mode of operation is when you run Makeflow inside of an allocation. So the Makeflow command is not run by yourself on the login node, but rather in a submission script, exactly the same way we've seen how to use Makefile, the GNU Make, inside the submission script. So here, the workflow is rather than the user submits a job to Slurm, and Slurm starts the job, which in turn starts the Makeflow. And when the Makeflow is done, Slurm knows that the job is done, and it's notified the user that the job is done. So an example is like this one. You see a basic submission script for Slurm, some sbatch parameters here, and you see that just like Makeflow has a -j option where you can specify the maximum number of rows that can run in parallel. And typically you will want to make this correspond to the number of processors that you have chosen. So here I submitted a job where I requested 4 CPUs. And so the slurm and prox here variable will be 4. And the ID with this -j option is to make sure that Makeflow does not try to create more processes than we have CPUs available. So I will not spend more time on this because it's very similar to the way you would use Make on the cluster, and the idea is simply to use a global allocation to make all the steps. And of course, this makes sense when the duration of the steps is relatively short, and rather if the duration of the steps is very long, you would prefer the other way around, so to have Makeflow submit the jobs to the scheduler. The third mode of operation is with Workqueues, and you will see here that the idea is a bit different. Makeflow will not submit jobs here, rather it will wait and listen for workers' registration, and you will have to start the workers manually. So if I take the same type of graph as before, the user starts Makeflow, and then at the same time submit jobs to the scheduler. And then when the job starts, it reports back to Makeflow that will respond with some tasks to run. And when the tasks are done, Makeflow is notified, and it's notify in turn the user. To submit a Makeflow like this, you use the capital T WQ. So here WQ stands for Workqueue, of course. You will see again a prologue, just like the other times, but here the distinguish factor is you see here this sentence that says that it's listening for workers on port 913. This is a default TCP port to which to listen, but you can of course choose the one using the command line options. Then it will submit a job directly. The first job again is rule 4 because it has no dependency, and at this point it would just wait for workers to register. So with that running on a terminal, you would start another terminal where you would run the command to submit the jobs. And Makeflow comes with commands to submit jobs with workers to all the typical schedulers that exist. And so here with the slurm, the program is called slurm submit workers. It will require 3 parameters. The first one is the name of the machine on which Makeflow was started. So let's assume here it's the front end of the cluster. It will ask for a TCP port to which it is listening and the number of jobs to submit. Here I ask for 2 jobs, and you see that this little script has started 2 jobs and submitted them to Slurm. And indeed, if you look in the queue, you see that I have 2 jobs that are waiting. Their names is WQ worker, and when I took this capture, they were in state pending. As soon as one of them or both are starting, they will register, and you will see that they will do the job, and you will see very soon job 1 is completed. As soon as job 1 is completed, again, Makeflow will submit the other jobs, but actually they will not be submitted to other jobs, but they will be gliding, as we say, inside the allocation that is already running. So the Makeflow system will distribute the work to all the jobs that are currently running and that have registered. At the end, as you would expect, it says that nothing was left to do. You can also, if you want, specify options when you use the slurm submit workers with -p, and you can say, okay, I want the jobs to run on the debug partition. So in Slurm, that will be -p debug or -- partition debug. But if you would like to mention here the specific number of gigabytes of memory to allocate and so on, you can put it there. Or you can use the environment variables defined by Slurm to achieve the same solution. You can also start the worker manually. So if you have some resources on the computer where there's no scheduler, you can use the Workqueue worker command, which has also which also needs the name of the machines on which Makeflow is currently running and the TCP port where it's listening. And then you see that worker will advertise the resources to the Makeflow, and then it will connect. You see that as soon as actually the Makeflow is finished Workqueue will disconnect, but also there's a timeout if for whatever reason Makeflow never asks the worker to stop. So this Workqueue system is called also pilot jobs in some other tools, actually enables resource pooling from multiple clusters. As long as you have a machine where Makeflow can run and can listen from connections, you can actually have the kind of situation like this, where the user starts Makeflow on some computer and then submit jobs to one cluster and also to another cluster, for instance. And then as soon as the jobs start on one cluster, they will register to Makeflow and ask for work to do. As soon as the jobs on the second cluster start, they will also register to Makeflow and ask for jobs to do. And if you remember, I said earlier that Workflow would copy the files to and from the workers unless you use the -- shared file system option. So here you don't need to worry about the files being copied back and forth. But of course, it can take some time to copy files, so it's sometimes a good idea to have them already available on the clusters. But in a way, this is a good way to pool the resources if you have access to multiple clusters. And of course, one cluster can be running Slurm and the other one can be running PBS. From your point of view, it will be totally transparent. But when you do that, of course, you need to manage the infrastructure of the machine where Makeflow is running, and you need to be, as I said, beware of data transfers, but also be cautious of security, and you need to make sure that not everyone can actually register anything to your Workflow instance. So until now, we've covered a few topics like installation, syntax, how to run and monitor jobs, and how to interact with the schedule. And I'm looking at chat if we have any more questions, and I don't see more questions. So then I would like to add a few topics to the talk. And you see here, I would like to talk about another syntax, and I will speak about nested workflows and Singularity. Because actually, the make syntax is not the only one that can be accepted by Makeflow. Makeflow also has a JSON-based syntax, which is less easy to the eye for the human, but is actually much more convenient for machines. And if you need to generate workflows with a machine, with a software, this is much easier to generate than the Makefile syntax. You see here that you can define variables in a define section. And here again is the exactly same example as before, except that the format is JSON and not Makefile. And you see a rule sections where you have inputs, outputs. So the outputs is a target, the inputs are the dependencies. You see the syntax is much more verbose than with a Makefile. So it's not, as I said, it's not meant for human, but it's meant for computers, for software. And you see here a construction where the variable is used to create the command line, and the effect is exactly the same as before. If your workflow is defined as a JSON file like this, you can use a --gx option to specify that the file here is not a usual Makeflow file, but it's an GX file. And so there's an X here because actually it's an extension of JSON, and we show an example just afterwards. But let me remind you that this is really machine friendly because most languages have JSON libraries available. So if at some point your program, your workflow is too complicated to actually write by hand, you can write in any language you want the program to generate the workflow description in JSON and then feed that to Makeflow that will do what it needs to have the final result. And of course, you can generate the JSON file from the Makeflow file. And actually, it's the same tool that I used earlier to generate the graphical representation. Here, rather than specify dot as output, I specify JSON as output. And actually, this will create a JSON equivalent of the Makeflow file. This is nice to play with it and have a look at the syntax. As I said, it's not purely JSON. There are some extensions like this one, for instance. If you remember, there are two rules in the make files that are very similar, and the difference is only the type of option that we pass to gzip. And here you see that there's a template function that is available, and you can use the for syntax for p in something, and this syntax is very similar to Python for those of you who know Python. And actually this allows in one syntax to define actually two rules. And so you understood already that the p here is referenced here with this curly braces syntax, which we've seen a few times already. And so with the template command, this will be replaced with best once and the other time with fast. And so this is a nice way to make the Makeflow file more compact. Here is another example where I use again the for loop here, but here I specified the range as a variable which is defined here, and I use again the template command here to use the curly braces notation, but actually you can also use string concatenation like this. It will work. So this will specify an output, which is directory / file, and then 1 for the first, and then .txt, and the second one will be file2.txt, the third one file3.txt. If I pass this to the utility to create the dependency graphs, you see that here I have those 3 files that appear here. Okay, so this was to show you that even though Makeflow was designed to cope with makefiles, if at some point a makefile is not sufficient because the workflow is so complex that you need a software tool to generate it, rather than trying to generate a makefile file, you can generate a JSON file, which is much more convenient given the fact that nearly virtually all languages have a JSON library. So second topic I wanted to talk about is nested workflows. So when you have a workflow where one of the steps is itself a workflow. In the Makeflow syntax, it would look like this. So simply using the Makeflow in capital keyword here will say that the rule here has a sub workflow. And you see here that the sub workflow in question is the example I've been using in the rest of the presentation. And you see a second rule that creates a comparison.txt file based on the 2 files that are generated by this Makeflow file, and I do a comparison of the sizes of the files, just for the sake of the illustration. So if you submit this with Makeflow, you see that something interesting. Makeflow will in turn invoke Makeflow itself with -t local. So if you ask Makeflow to submit your job to the cluster, the sub workflows, the nested workflows will actually be run inside the same allocation. So you will not have jobs that spawn other jobs. And another thing which is interesting with Makeflow is that the cleaning works recursively. So if you run Makeflow and then the name of the Makeflow file where there is a nested workflow with --clean, you see that one of the operations is cleaning the sub workflow. And so Makeflow will call Makeflow --clean recursively. So again, if you want to clean everything, it will do it for you in a way which is intelligent. This was the syntax for nested workflows with the Makeflow syntax, but also, of course, you can use it with the GX syntax. Simply replace the command keyword with workflow keywords, and here the name of the Makeflow. This is equivalent to what I've shown earlier. So do we have any questions about these parts? So the nested Makeflow and the GX syntax? No, then I will move on to the last part of this short talk, and it's about Singularity integration. So I will not explain Singularity or Aptainer, as it's called now, in details, because it will be the subject of Olivier's talk tomorrow morning. But basically, it's container for HPC. So you can see it as a cluster-friendly Docker if you know about Docker. And if you only need to understand one thing about Singularity, it's that it's an easy way to pack and deploy software with all dependencies. So basically, a container is just the idea of having nearly an entire operating system inside a single file. And then you can run commands on that file as if it were run on a machine where that operating system is installed. So here, if an example where I am on a CentOS cluster, so CentOS is a very popular Linux distribution for clusters. If I look at a file called HC something release, you see that it says it's a CentOS cluster, release 7.9, for instance. Now, if on that cluster I have a image file called lolcow, for instance, .sif, and sif stands for Singularity image file, that holds an Ubuntu image, which is another very popular Linux distribution, but more popular on laptops and desktops than on clusters. You see that actually running the head command, the same head command on the same machine, but through Singularity specifying this file, you see that the output is that it's a Ubuntu. So the head command is run inside the image file rather than directly on the cluster. So let's take my example here, which I simplified a bit, and you see here that I'm just using the head command again to see what kind of Linux version I'm running on. And by default, what you need to understand is that with Singularity, anything that is etc something, for instance, is taken from the image, while anything that is in the /home is taken from the cluster file system. Again, for the details, please attend the session tomorrow morning by Olivier. He will explain all of this in details. Here, what I just want to mention is that Makeflow has a -- Singularity option, which you might at some point rename to -- Aptainer. I don't know about that, but it's named Singularity in the current versions. You specify a Singularity image file, which again holds a complete operating system, and then the name of a Makeflow file. As you would expect, all the steps in the Makeflow are actually run inside this Singularity image file. And you see that at some point, Makeflow will create a wrapper file to run each of the step inside Singularity. And so the example run, you see the output here that shows that you are actually running into the Ubuntu image, even though the operating system that is installed on the cluster is CentOS. And sure enough, if you look at the files that are created in the directory, you see the targets that you would expect, even though actually the software that was used was inside of the image. So Singularity and Makeflow work together so that the targets and the input file are taken from the file system, while all the software and configuration is taken from the image file. So the idea with this integration is that you can install all the needed software in a Singularity image and then submit all jobs with the Singularity image on the compute node and possibly on multiple clusters. So here, thanks to Singularity, even if the target clusters are have very different operating systems, you can have a consistent environment for your jobs because Makeflow will carry the image along. Okay, do we have any questions? I'm looking at the chat and I don't see any. So I'm at the end of my presentation. I wanted to present to you Makeflow and how it's used. So what we've been talking about were how to install it. You see that you can install it like pretty much every other software that you use. We have seen that there are two syntaxes, one that is meant for humans that really resembles the one of GNU Make, and also a syntax that is a JSON syntax with some extensions that are really meant to be produced by software. In both cases, we can have variables defined and so on. We've seen how to run and monitor the output. I mentioned, and it's important, that Makeflow is blocking, so you have to keep it running for it to monitor the queue and submit jobs and so on. As a reminder, it has a make-like behavior, so it does not redo something that does not need to be updated. You can have also some tools that help with the graphical representation or syntax check and so on of the Makeflow, so you can make sure that the Makeflow corresponds to the study that you actually want to implement. And then I finished with a Singularity integration where you can actually carry along nearly a full a full operating system to run on the clusters. I also mentioned there are three ways that Makeflow can interact with the scheduler, with -T slurm, where Makeflow will submit jobs to the scheduler, -T local, where you will actually start Makeflow inside of a submission script, so inside of an allocation. And I've talked about work queues, and the fact that you can actually use work queues to spread the workload across multiple clusters. Finally, I've been talking about nested workflows and the fact that Makeflow has some features in it to actually flatten nested workflows and make sure that everything goes smoothly. So this is it for today.